and Lawrence Berkeley Laboratory as postdoctoral fellows before she moved on to the theory group of Brookhaven National Laboratory as a senior scientist in 1994. She also headed the group for a few years, and later she became the divisional head as well. She is an adjunct professor at the Young Institute of Theoretical Physics at Stony Brook University. She is a theorist who has been working on Higgs and collider physics for many years, including precision calculations for the LHC. You can imagine that a few decades back, one of her studies concerned looking for Higgs boson in pion and kaon decays. So she is really the master in these fields. So in the early 80s, if I remember, as the gauge boson sector of standard model was getting verified in experiments, search for the Higgs boson became more intense in LEP and tevatron experiments. And she was one of the authors for the very famous book, Higgs Hunter's Guide, which got published in 1989 or 1990, I think. So yeah, of course, it was very popular, and it became almost a Bible for all the collider physics graduate students, at least. In 2004, she was the chair of the Division of Particles and Fields of the American Physical Society. She has, of course, many accolades. I would mention only maybe one more. She received the Sakurai Prize of American Physical Society in 2017 for her instrumental contributions to the theory of the properties, reactions, and signature of the Higgs boson. I have seen her, fortunately, in Leju's workshops, how intensely and the collaborations going on. So I am really excited to hear from her. She continues, of course, addressing important and timely issues in Higgs physics. And today we shall hear about the EFT analysis in Higgs sector. So I stop here and I give the floor to Professor DAWSON.
Okay, you should see my screen now.
Yes.
Okay, so it's a pleasure to give these lectures. I'm sorry I can't be there in person to give them because it's always more fun to interact and meet the students at these schools. But this is a very interesting school that has been set up here. And it really makes the point that effective field theory connects all kinds of physics. You've already heard from John Ellis on global fits and EFTs. You've heard from Eleni and EFTs for top quark physics. And you'll see from my lectures that I'm going to talk a little bit about top quark, global fits, because you can't separate these things cleanly. So this is kind of fun. And what you're going to hear from me, I've got way too many slides, so you probably won't see them all. But what you should take home from my lectures is that the EFT, it's beautiful and it's glorious, but there are a lot of little assumptions that keep creeping in. It's not really a model independent way of looking at physics. So one thing you should take home is the questions you should ask when you're thinking about EFTs for Higgs or top or global fits, how you should poke at the studies. So we all know that the particle physics world is not the way it was a decade ago, because now we've found the Higgs boson. The standard model looks like it's pretty good. So why are we even doing EFT physics? So this is a time of thought and retrospection for the theory community. We've got the European strategy study just completed a few years ago, and the SNOMAS study in the US, making us think about the future and really what we're missing from our knowledge of the Higgs boson and how to go about learning more about the Higgs. So I always like to show this picture just to make the point that things have really changed dramatically. We found the Higgs, and it really looks like it's a standard model Higgs. We have absolutely no evidence that it's not the standard model. So the standard model is simple and predictive. I'm not going to describe the standard model here, but writing it on this mug is not really, false. This Lagrangian on the mug is a standard model. The standard model is really, really simple. It's almost the simplest thing you could write down. And that makes us wonder, why on earth is the world that simple? The world seems complex and complicated, but yet we've got this model that's so simple. It's the SU3, SU2, U1 gauge theory, to the best of our knowledge. The electroweak sector is described in terms of the masses of all the particles in 3 inputs. Typically, we take these inputs to be G Fermi, alpha, and MZ, but you can swap these around. Oops, sorry. For G Fermi, MZ, and MW, all the particle couplings to each other are fixed. So the only unknown parameter is the Higgs. So this is a model that we can test, and we can test deviations of this model. So let me just review the Higgs couplings here. They're all known is the point. The couplings are proportional to mass. So the couplings of the Higgs to fermions are the mass of the fermions. The couplings to the mass of gauge bosons are the Higgs WW is MW squared and Higgs ZZ is MZ squared. The couplings to the massless gauge bosons arise at one loop. Again, they're absolutely predicted, and they look like G mu nu H or F mu nu H. So we know what they are. The Higgs self-couplings are proportional to MH squared. So again, this is a very powerful theory with only one free parameter, the Higgs mass. So how do we make the Higgs boson at a hadron collider, say the LHC? The most, or the dominant way we make the Higgs is glue goes to H through a top quark loop. So of course, this is interesting, this production mode, because if there's some new physics, say a stop from supersymmetry or a heavy top, it would contribute in this loop. So this is the most important process. Gauge boson fusion, Q prime goes to outgoing quarks and a Higgs with the exchange of W's and Z's. This is quite a small rate, but yet it's very sensitive. So the Higgs couplings to taus are predominantly found from this production mode. And you note that this production mode depends on the coupling of the WW to the Higgs or the ZZ to the Higgs. So this interaction would vanish if V were 0. So observing this kind of production mechanism is a fundamental test of the electroweak symmetry breaking. And of course, the associated production of the Higgs, QQ bar goes to a W or a Z plus a Higgs, is exactly the same Feynman diagram. So here's a WW Higgs. So this is turned on its side from here. And finally, there's TT bar H production. So glue goes to TT bar H, and there's also QQ bar goes to TT bar H. So you heard about TT bar H from Mullany because, of course, the top quark and the Higgs get connected through processes like this. So we want to ask the question, is there more? It doesn't look like there are more Higgs bosons. We haven't found them yet. So how do we tease more physics out of this picture of these very simple couplings, all predicted, these production modes, all of which have been observed at this point? So how do we go beyond here to know if it's a standard model with the Higgs, or maybe it's the standard model is just the low energy manifestation of some more complete model that exists at high scales? And this, of course, is where effective field theory comes in. So to think about effective field theory, you have to start with the idea of decoupling. If you have some new particle X with a mass, say mx, which is much greater than mw, okay, it contributes perhaps to the standard model. So the standard model has, say, QQ bar goes to QQ bar, or E plus E minus goes to E plus E minus, whatever. There's a Z exchange, and the exchange of a Z would go like some coupling constant squared times 1 over the mass of the Z squared. And the contribution from this new particle X, here we show, it would go like some coupling constant squared times 1 over the mass of this X particle. And so the scattering rate for whatever this process is would be the standard model rate here, plus contributions that go like 1 over mx squared, the interference of these two diagrams. And for mx goes to infinity, this goes to the standard model. So the effects of the new physics would vanish as 1 over mx squared for weak coupling. And this is an example of what's called the Applequist Kerosene decoupling theorem. And this is, of course, why it makes sense to analyze all of our standard model physics, even if there's something heavy at very high scales, because the effects of this X particle decouple as mx goes to infinity. But the really important and interesting point is that the Higgs is different, because if you go back here to this simple study, what it assumes is that the couplings of whatever new particle you have, say X, just goes like some coupling constant, Gx I called it here. But with the Higgs, the couplings go like the mass of the fermion that they're coupled to, or perhaps the mass of the gauge boson. So this is a non-decoupling effect because this spoils the simple counting that I had before. And you can see these non-decoupling effects of the Higgs, for example, in gluon fusion goes to Higgs, which I'll describe in gory detail as I go on. But for Higgs production, glue goes to H, the rate is actually independent of the top quark mass in the loop when the Higgs is much lighter than the top quark mass. And exactly the same way, if I look at the Higgs coupling to two W bosons, which is the mass of the W squared, for example, the polarization tensors of the outgoing W's here, if the W's are longitudinally polarized, it's just proportional to the momentum of the outgoing gauge bosons. And again, it does not decouple. So the longitudinal polarizations change the counting because they grow with energy. So I can no longer use my decoupling theorem to say, oh, this heavy physics decouples, because with the Higgs, these effects don't decouple. So this all suggests that the Higgs sector is a good place to look for new physics because the Higgs sector is fundamentally different. So let me give you my first EFT example in Higgs physics. And it's a counterexample or an example where there's non-decoupling. So it's a very familiar example, I think, to most people who do LHC physics. So I'm going to think about two gluons, a top quark loop making a Higgs. So this is something that graduate students now calculate as an exercise. So glue goes to Higgs. It's got a coupling constant. It's got some form factor here that depends on the Higgs mass and the top quark mass. And it's a delta function because the Higgs has to be on the same as the energy squared. So what if I take the limit that the top quark mass goes to infinity? What happens is that this goes to a constant. So glue goes to H, counts the number of heavy fermions in the loop. So it goes to some constant. So for every chiral fermion in the loop, this factor FQ here goes to -4/3. So it's independent of the mass of the fermion. So you can derive this result from a simple effect of Lagrangian. Suppose I take the gluon field strength tensor, G mu nu, so this is dimension 4 of the two G's, and just connect it to the phi dagger phi squared, the Higgs field. And then I put some factors of alpha S and V up front. So when electroweak symmetry breaking happens, phi goes to phi naught, so it goes to H plus V over the square root of 2 in the usual fashion. So this kind of effective field theory, this kind of interaction generates the heavy top quark limit of glue goes to H. Okay. So what does this mean for looking at Higgs couplings? So how do I look at Higgs couplings? How does the LHC study Higgs couplings? Well, in run 1, they looked at what was called the kappa rescaling. So one can just define some factor kappa I, which is a Higgs coupling to particle I, normalized to the standard model Higgs coupling to particle I. And this is the way run 1 Higgs couplings were studied. So there's a problem with this. And the basic problem is that this kind of study violates gauge invariance because, as I told you, the standard model is really, really simple. The standard model fixes all the couplings. In particular, it fixes the Higgs couplings to all the other particles, and it requires kappa equals 1. So the Higgs couplings are not free parameters in the standard model. So studying them as if they were free parameters violates gauge invariance. So this is not a consistent field theory doing this. It's not possible to include any higher order corrections because this is just some phenomenological model where I mucked up the Higgs couplings. Electroweak corrections in particular don't factorize and can't be included at all. There's no kinematic information by studying Higgs couplings by just scaling them up and down. So the fact that when we measure Higgs boson couplings, we measure distributions. And much of the information about Higgs couplings comes from how the shapes of the distributions change. But this kind of study can't take that into account. And in the worst part of it is, in this picture, the Higgs coupling measurements cannot be combined with other measurements. They stand by themselves. They're just measurements of perceived deviations from the standard model. So it's a good way to start thinking about Higgs couplings, but it's not really very satisfactory. But now we know that the Higgs couplings are really close to the standard model by doing this kappa analysis. So here are these kappas, which are 1 in the standard model. So this is just the deviation of the overall coupling of the Higgs from what's measured. So here's 1. So the line up here, and they show various uncertainties, but you can see it's pretty close to 1. And you can also see at the time that this plot was made that the sign SIGN of the coupling to the top quark had a little possibility of being the opposite sign. And here's the similar plot from CMS showing the extracted couplings of the Higgs. So here's mu, tau, b, w, z, t. This has 137 inverse femtobarns, so it's a relatively recent plot. And if you look at the ratio to the standard model, the Higgs couplings pretty much lie on a line of 1. So this suggests that we need to go beyond the kappa framework to see if we can tease out more physics from the Higgs measurements, because we know that the standard model requires these couplings to be 1, but this kappa framework doesn't let us do any radiative corrections, doesn't let us take into account the kinematic distributions, doesn't let us connect with any other measurements. So this is pretty much all you can learn from the kappa framework, that the Higgs couplings are close to 1. So that's not tremendously useful. So we want to go beyond and use an effective field theory. So when I'm looking for the new physics, we can either find a light resonance, say I've got a 2 Higgs doublet model, I can find the second Higgs, that would tell me I have new physics, or I can use precision measurements and effective field theory. And this is, of course, the subject of this school, using precision measurements of Higgs couplings and interpreting them in the light of effective field theory to get more physics out than we got from just measuring Higgs couplings alone. So you've seen slides like this before, since I'm in the middle of this school, but the effective field theory makes some assumptions, which I want you to keep in the back of your mind. And one of them, of course, is that whatever this new physics is, it's at some scale lambda, which is much, much bigger than MW. Because, of course, if the new physics were at a low scale, we would have seen it now. We would have seen a 200 GeV second Higgs or whatever. So this new physics is assumed to exist at some very, very high scale. So whatever is going on is up there at the scale lambda. So this is a very sad scenario. And in fact, effective field theory is really kind of the last resort. We'd really rather find some new Higgs particles. So effective field theory just assumes there's nothing, that there's only the standard model particles at the low scales. And the only way we can learn about very high scale physics is by these effective operators and global fits, which you heard about from John Ellis. So the standard model effective field theory assumes the SU3 cross SU2 cross U1 symmetry and standard model particles only. So at this stage, it's a beautiful model independent study. We assume the Higgs is in an SU2 doublet, but that's really all I've assumed right now. So the new physics is described by a power series expansion in 1 over lambda squared, 1 over lambda cubed, 1 over lambda to the 4th, and so forth and so on. These operators L5 and L7, which are odd in lambda, are lepton number violating. So when we study LHC physics, we typically start with the dimension 6 operators, this L6 over lambda squared. So this is exactly what I was describing in my simple example of decoupling. I have this very heavy particle X, say it's at the scale lambda, and the first effects I see of the particle X are 1 over lambda squared. So that's an example. I can map my heavy particle X to my effective field theory and get the terms in my effective Lagrangian. So all the new physics effects are contained in these coefficient functions C, and these operators O are a complete basis. And I'm sure you heard about constructing this basis from Michael Trott. So there are a lot of advantages of the Smeft approach practically from Higgs' point of view, because this is a quantum field theory. It's a consistent quantum field theory. So I can compute the cross sections without knowing the high scale of physics. I can compute them as a power series in 1 over lambda squared, and it's systematically improvable. So as Eleni talked about in her top quark lectures, you can calculate, for example, the QCD corrections. So you can improve the simplest calculations of the Smeft with the higher order corrections in QCD. So at this level, the Smeft calculations are model independent. And then the measurements are always interpreted in terms of the Smeft coefficients. And then you can compare different classes of models. So of course, this sounds very good, but of course, all the details really matter here. So let me just point out a nice review down here if you need to learn more or are interested in more effective field theories. So the first thing you have to do is find a basis of operators. So if you start with the dimension 6 operators with no assumptions, there are 2,499 possibilities. And of course, nobody's going to do a fit to 2,499 operators. So the most popular basis is a Warsaw basis, and this is pretty much used by all the experimentalists studying top quark, Higgs physics, whatever. So I'm going to work to the tree level mostly with one occurrence of the dimension 6 operator. So that would be to think about things that have the operators that occur at dimension 6. They're suppressed by 1 power of 1 over lambda squared. And so now if I want to go from all these operators to something that's reasonable to make fits to, here's where the assumptions start coming in. So typically in the fits that John showed you, what he has done and what pretty much everybody does is to consider the contributions to processes which are dominated by the Higgs resonance, by the Z resonance, by the W resonance. And after you consider this, you consider the interference with the standard model. So you consider the linear terms in the effective field theory. So this is all completely reasonable and reduces the operators to some number on the order of 30 or so, depending on flavor assumptions. So if you make different flavor assumptions, you get a different number of counting. But you can see that by making these flavor assumptions and by making these assumptions that most of the important physics is going to come from the resonance contributions, you get something where you can actually do experimental fits to this. So you're getting something practical. So here's the Warsaw basis. You've seen this before. There are lots of operators. But what I want to make the point of is that the interesting operators are those with derivatives, because the derivative operators introduce new structures into the kinematic distributions. So now we've done something that you can't do within the Kappa framework studying Higgs physics. So now we have operators which come at dimension 6, which contribute to Higgs processes, which have derivatives. So then they have momentum dependence. So the Higgs mechanism in Smeft. There's nothing new about the Higgs mechanism in Smeft. It works exactly like in the standard model. So the Higgs Lagrangian is d mu phi dagger d mu phi. So this is the standard model Higgs kinetic term. There's a mu squared phi dagger phi term, and then there's a lambda phi to the 4th term. So this first line here, this is the standard model. So since I say I'm going to work to order 1 over lambda squared in the Smeft, there are terms which contribute only to Higgs physics. So there's a term here, phi dagger phi cubed. Okay, there's this guy. There's a term CH box, which is phi dagger phi box phi dagger phi. So here are derivatives here. There's a term CHD phi dagger d mu phi, phi dagger d mu phi. So again, they're derivatives. So for example, let's look at this term CHD here. So if you put the phi dagger here and the phi dagger, the phi dagger here, both to V. So put these guys to V. So this is V squared d mu phi, d mu phi. So this gives a contribution to the Higgs kinetic term. So with the introduction of this operator, the Higgs kinetic term is no longer canonically normalized. So if I define phi as usual, so the minimum here is V plus, I'm going to call it H naught for the moment, 1 over the square root of 2. And here's the goldstone up here. So minimize the potential exactly like in the standard model. So here's V is mu squared over lambda, and then it's got a contribution here, which has a funny form, but it depends on this operator, C to the 6 up here. So minimizing the potential, the kinetic terms are different from the standard model, but there's nothing complicated. So the Higgs field is not canonically normalized. Here you go. Here's the d mu h naught squared. It's got this extra term from CH box and CHD here. Here's the extra terms contributing to the Higgs mass. So you can canonically normalize the Higgs field by shifting the Higgs by a factor ZH. So here we go. The Higgs is shifted 1 plus V squared CHD and so forth. So I shift the Higgs field to make this term canonically normalized. So there are other possible purely scalar operators, which you don't see. You might think to write them down. But since the Warsaw basis is the complete basis, they can actually be eliminated by integration by parts or by use of the equations of motion. So the gauge sector also, there's nothing new about it. It's exactly like in the standard model with some extra pieces. So again, one shifts the fields so that the gauge fields have a canonical form and canonical energy, kinetic energy, find the masses exactly like in the standard model. And so here I've written down the expressions for MW and MC in terms of the gauge couplings. So the bars on top of these G's here are to remind you that these are the G's, the couplings in the Lagrangian I started with. So MW, it's GV over 2. So this looks exactly like the standard model. However, the Z mass, here's the standard model piece here, but it gets contributions from these new operators, CHWB and CHD. So the form is not important to remember, but what's important to remember is that now the relationships between the Lagrangian parameters and my physical parameters are changed in the Smeft. And so one has to be consistent. So the bars here remind us that when I'm turning things into MW and MC, I get these extra pieces here from CHWB and CHD. Okay, I didn't put a reference here, but in point of fact, I think somewhere in my lecture notes, I have a reference to the Feynman rules in the Smeft, which are extremely useful. And you can look at these forms and see what they come out to be. So let's talk about what this does for Higgs physics. So let's start with Higgs goes to BB bar. So I want to look at the total width of the Higgs to BB bar normalized to that in the standard model. In the old days, I would write this as 1 plus delta kappa B quantity squared. So in the new world, I'm going to write it in terms of Smeft operators, Smeft coefficients. So delta kappa B, G Fermi lambda squared. Okay, here's the overall coefficient. So it depends on a bunch of these dimension 6 coefficients. So I've written them down here. So let's look at what they are. The first two, CH box, CHD, just come from normalizing the Higgs kinetic energy. So it has the canonical and required form. Okay, so we know what this is. The second two terms come from this relationship, from the change in the relationship between G Fermi and V. As I mentioned in the previous slide, the relationships between the physical parameters, G Fermi, MW, MC, are changed in the Smeft. So this accounts for the fact that these relationships are changed. And then there's the contribution from a new dimension 6 operator that's contributing to H to BB bar. So here it is. This particular operator is suppressed by 1 over MB in this decay rate. But now if you stare at this thing, you're skeptical because you say, is this just a fancy way of writing the kappas? Because this looks like delta kappa B. Sure, I wrote it in terms of all of these Warsaw coefficients, but that's really just a number. So it doesn't, at this point, it doesn't seem like we've gained much. But now let's go on to Higgs to ZZ. In fact, the most precise measurements of Higgs couplings at the LHC come from Higgs to 4 leptons, where the 4 leptons come from ZZ. So the first line here is Higgs to 2 on-shell Zs, so it's not a physical process. And the second line here is Higgs goes to an on-shell Z into 2 fermions. So the second one closely approximates what the experimentalists do because their cuts put so that they know that these 2 fermions come from a Z. So I can calculate this ratio in the Smeft exactly as I did for BB bar. So this ratio, 1 plus some terms, and these terms depend on Smeft coefficients. So let's look at the first term. The first term, which I've called little c sub k, is the same whether they're on-shell Z's or one of the Z's is off-shell. And this c sub k is just exactly the same combination of coefficient functions that arose for the decay of the Higgs to B's. So this looks just like a rescaling of the Higgs couplings to Z's, this c little k. However, this second term, which I've called CZZ, has a coefficient here, which is different. I've circled it. It's different for on-shell Z's and one of the Z's off-shell. And this coefficient, CZZ, depends on many of the other coefficients, CHW, CHB, and CHWB. So here we go with the CZZs. But the thing that we've learned here is that the number here, this 0.97, multiplying this combination of the coefficients, depends on momentum. So if I think about H to Z FF bar, so this is the ingredients of Higgs to 4 leptons, I'm getting more information from using the EFT than just rescaling the total rate. So suppose Q squared is a fermion pair invariant mass squared. So Q squared is the FF bar invariant mass squared. So now I can write d gamma dq squared in the EFT as a standard model piece, as I always do. And here is this piece that simply rescales everything. So this is the piece that corresponds to the kappa terms. But the next piece has an explicit factor of Q squared multiplying this combination of coefficient functions. And there's a bunch of stuff here. So the coefficient of CZZ, this bunch of stuff here, depends on Q squared, and it's a function of the experimental cut. So I've just drawn the graph here, which isn't that important. But the point is that now I've incorporated into my fit the kinematic dependence, the Q squared dependence, the cutoff dependence of the measurements. So when I look to measure H to Z FF bar, this thing, this 0.97, depends on the kinematics of the study. So by doing the fits to these coefficients here, I'm learning more than I learned from simply rescaling the Higgs couplings. Okay, so now let's go back to gluon fusion again. And let's think about gluon fusion in terms of the Warsaw bases and doing a total fit to Higgs couplings. Well, at lowest order, there are 2 operators that contribute to the gluon fusion production of the Higgs. One of them is this operator OHG, which was the operator I wrote down at the beginning, G mu nu squared, phi dagger phi squared. Here it is right down here. So this was the operator I wrote down when I was talking about the Higgs not decoupling. So here it is contributing at order 1 over lambda squared to the gluon fusion of the Higgs. And then there's another contribution, which I've called CTH. And here it is, CTH here. And if you stare at this, it looks like a rescaling of the Higgs of the top quark Yukawa coupling. So Q bar left, phi tilde T right. This is the top quark Yukawa term in the standard model. So if the phi has a V, this would just be a contribution to the top quark Yukawa coupling. But since there's also the contribution from the Higgs and the phi, this introduces new interactions. So what this does by starting with this effective field theory in gluon fusion, it changes the relationship between the top quark mass and the standard model Yukawa, because this contributes to the top quark mass. So the top quark mass is a standard model Yukawa. Here we go, the standard model Yukawa, plus a piece that comes from the effective field theory, CTH. And this changes the TTH coupling. So here we go. The TTH coupling is changed by the fact that we have this effective interaction here. And so now you can see the direct connection between, say, Higgs physics and top quark physics. because I'm using this simple effective field theory Lagrangian here to talk about glue goes to Higgs. But Eleni told you about TTH production, which also is sensitive to the same operator. So already you see that Higgs physics is connected to top quark physics. You can't separate them. So what does gluon fusion measure? Well, it cannot distinguish between these two coefficients in the large M top quark limit, because as I showed you in the large M top quark limit, in the standard model, this kind of operator goes to 1. So the amplitude for gluon fusion goes to Higgs. It's got a standard model piece, but then it's got a piece from this CHG. CHG is just this phi dagger phi times the gluon momentum. And then it's got a contribution from a term like this, which looks like a rescaling of the top Yukawa. So it cannot distinguish between these two possibilities. And this kind of flat direction is very, very common in the Smeft, because many of these processes depend on various combinations of the coefficients. So for example, that's when John Ellis showed you the global fits, he's able to eliminate these kind of flat directions by fitting to many, many processes. So for example, gluon fusion to a Higgs depends on this combination, but now if I did a fit to glue goes to Higgs plus jet, then it would depend on a different combination. So it's only by doing these global fits that I can eliminate this kind of flat direction. So here we go. We're going to do a fit to the momentum dependent operators. So this is the Higgs plus jet production. And here we go, the PT of the H. The black line is the standard model, and the lines around it are changing these two coefficients, CHG and CTH. And one of the really bad things about the effective field theory community is that there are a lot of notations in the world. So this plot, for example, uses different normalizations for these coefficients from the normalization of the Warsaw basis, but they're exactly the same operators in this plot. And what you can see is this dependence on the kinematic structure that I was advertising as the power of the Smeft for Higgs physics. But the other thing you can also see here is that if you go out to 800 GeV, for example, high PT, you see that there's a very large change in the rate. This is a logarithmic scale here. So this is an order of magnitude you get by changing these coefficients. So you can get very large effects here. And so this opens another question of making sure that the effective field theory is actually valid. Whenever you get huge effects, you have to think, well, am I violating unitarity? Am I violating the perturbative expansion? Does this make sense? So let's start by trying to identify these two Smeft coefficients. So I want to know if it's a TTH coupling or if it's this glue Higgs effective coupling. And I want to know by looking at things like the distribution of the Higgs. So here is a recent plot from these folks down here. And I've just written, here's a non-standard model GGH coupling, and here's a non-standard model TTH coupling. They're exactly the same operators, but their normalization is different, unfortunately. So here's what you get from measuring the Higgs PT. You get this circle here, this gray circle. Here's what you get from measuring TTH production. It's flat in the GGH coupling here because that only enters in at loops in TTH, and it's a very small contribution. And the standard model is right here. So by putting together these two processes, you would swipe out this little circle in the middle, and you would learn something about both of these operators. So the projections when I go to the high Lumi LHC are actually very, very interesting, because here again is this coupling of the Higgs to the gluon, and now the normalization is the same as mine. And here's the TTH anomalous coupling, so the vertex contribution here. So here we go. Here's what you would learn from TTH production at the high Lumi LHC. These blue lines are what you would learn from just measuring the overall rate. So this is a straight line here because it's not sensitive, of course, to anything other than a combination of the two operators. And this circle here is what you would learn for measuring the Higgs PT. And again, you can see that by measuring this combination of processes, you can really learn something about these operators. So that brings me to the question of when is the effective field theory valid? We get these really neat effects, but are they really valid? So I've described the effective field theory as a power series in 1 over lambda squared. But of course, the next term in the 1 over lambda squared is dimension 8 terms 1 over lambda to the 4th. So in the Smeft and in the global fits, what one typically does is expand in terms of powers of 1 over lambda squared. So here we go, the standard model piece, the dimension 6 piece, and so forth and so on. So to just include the dimension 6 pieces, I get the standard model, I get a 1 over lambda squared piece from the interference with the standard model, and I get a 1 over lambda to the 4th from the square. So you instantly see that there's a problem. And the problem is that these terms, which I'm typically dropping when I do a fit, are the same order as these dimension 8 pieces. So if I'm going to include these 1 over lambda to the 4th terms from squaring my amplitude, then I have to have some argument for why I didn't include the dimension 8 pieces. And if I drop this 1 over lambda to the 4th pieces, well, then I've calculated only the interference here. So I can get negative cross sections because I haven't calculated an amplitude squared. So you can see that there's a problem here. I calculate consistently to 1 over lambda squared. I can get negative cross sections, and that's no good. I include the amplitude squared with dimension 6, but then I have to explain why I didn't include these terms. So this leads to the idea that there's some maximum energy where the Smeft is valid. And there are various schemes for understanding which terms to include. So in point of fact, there is no agreement in the community about how to do this. And I think that's a fair thing to say. The community is struggling with understanding how to do this. So there's a certain counting law that you can make simplistically. You can say that the standard model contribution goes like some coupling constant of the standard model, say G weak, and the dimension 6 pieces go like some BSM coupling, GBSM. And so then when I start squaring things and so forth, what happens is that the 1 over lambda to the 4th pieces, which I'm worried about, they're of the same order of magnitude as the dimension 8 pieces if the coupling of GBSM is sort of the same as the standard model. But if GBSM is much, much bigger than the standard model piece, then the dimension 6 squared pieces could dominate. So there's a scenario where it's completely consistent to calculate to dimension 6, square the amplitudes, drop the dimension 8 pieces. So one has to think about this when one is arguing for what to include in your fits. Okay, so let me see here. All right, so let me just point out that the standard model is special at high energy. In the standard model, there's a cancellation of terms which grow with energy at high scales. So for example, let me talk about W plus W minus goes to W plus W minus. And of course, you all realize that this is just vector boson scattering if you stick some quarks on these W's here. So there are a lot of contributions here, and this has been known since Lee, Quigg, and Thacker, probably, I don't know, 50 years ago. So these terms have contributions which grow with energy to the 4th. This kind of interaction has terms which grow with energy as e to the 4th. And between the top line and the middle line, the terms which grow like e to the 4th cancel. Now, this middle line also has terms which grow like e squared, and the exchange of the Higgs has terms which grow like e squared. And the contributions of the standard model are exquisitely tuned for some reason so that these terms which grow with energy cancel. So in the standard model, unitarity is conserved. There are no terms which grow with energy. But of course, in the Smeft, that's exactly what we're doing. We're messing with these cancellations because if I change the Higgs WW interactions here, I'm changing the cancellations, and I no longer have these beautiful cancellations. And you can see that you're going to get limits on the Smeft coefficients where they violate unitarity. Okay, so now I'm going to skip. Well, let me put this. The Higgs couplings to gauge boson. Oops, let me talk about the Higgs couplings to gauge bosons before I skip to the who cares part of my talk. So there are operators that contribute to the Higgs couplings to WWZZ. I've written them down here. And you should notice that these couplings depend on momentum. So d mu phi, d mu phi. So here I have interactions that are momentum dependent, exactly the interactions that are going to give me sensitivity to the kinematic distributions of the Higgs. So the effective field theory effects are going to be enhanced at high energy and high momentum transfer exactly because of these derivative operators. And these derivative interactions can change the kinematic shapes. However, there's a problem with this study. And the problem is that once I start messing around with the Higgs couplings to WW, well, the same operators that contributed to H to WW also change the ZWW interactions, and also the QQ bar Z gamma interactions are changed. So I can't look at Higgs physics in a vacuum, just like I couldn't separate glue goes to H from glue goes to TT bar H, which then works its way into other top quark physics. Once I look at Higgs decays to gauge bosons, I've also got to look at Higgs decays to dibosons because it's the same operators coming in. So this has led to the concept of global fits, because once I look at Higgs physics, then I spoil the WW pair production, and I've got to look at everything all together. So because of this unitarity cancellation, in the standard model, there's no growth with energy, but now in the Smeft, there is a growth with energy. And I like to point out that this is a very, very old story that started in the LEP days with Hagawara, Pache, Zeppenfeld, and Hakasa. And it's exactly the same story in the Smeft. You change these vertices, you change everything. So once I look at these effective field theory effects on W pair production, I get this problem that I was mentioning with the negative cross sections. So if I only include the 1 over lambda squared contributions to W pair production, I get this blue line here. You see, here it goes negative because, of course, it's not consistent to only consider the linear expansion. So in the fits, typically what happens is that we just throw out these points where the expansion goes negative. So if I include these 1 over lambda the fourth terms from the dimension 6 operators, you get huge effects. So over here, you get these effects which grow immensely at high energy. So there's a huge difference when I do the fits between doing fits, which I've done to including the 1 over lambda squared pieces and the 1 over lambda the fourth pieces. And this comes up everywhere. So now I'm going to skip, because you've heard much of this and you can look at this at your leisure. You heard from John Ellis about the global fits, and now you can see the quadratic are the blue and the linear are the orange. So you can see this is a log plot. The importance of how I do my expansion. Down here, there are all these operators which depend on making a choice of how I do my fit. And you can see that the precision that you measure the operators varies 10 to the minus to 10 to the third. So one thing I want to point out here is that if I just do only a single operator, I get very, very different effects. So you have to use the power of the effective field theory and do fits, do these global fits. Because if I tried to look at Higgs physics by itself, and I only looked at one operator that occurred in some Higgs process by itself, I would get much stronger bounds than the global fits get. And that's because there are all sorts of cancellations and interactions that occur in the global fits. But to me, the really interesting question is, what do we learn by fitting these effective field theory couplings? because of course, you know, when we did the fits at LEP, we measured MZ very precisely. We measured couplings to the B quark very precisely. And these were things which were predicted in the standard model. So we had a target to shoot for. So we could measure the consistency of the standard model by these very, very precise measurements. But now it's different. Now, if I'm measuring an effective field theory coefficient, I don't know what it is. It's a free parameter. So the important thing to me is, what do I learn? If I actually ever measured some effective field theory coefficient that was statistically significant to be not equal to 1 or not equal to 0. So does that tell me anything? So the point is that in any given high scale model, the coefficients of this effective field theory are predicted in terms of some small number of parameters. So if I have my model at, I don't know, 10 TeV, 100 TeV, wherever I think the 2HDM is, or the Higgs singlet model or whatever, I'm going to know what the coefficients are. And I'm going to generate different operators in different models. So the dream of the EFT practitioner is that not only will I measure some coefficients that are not 0, but I'm going to measure a pattern of coefficients. So I will have some pattern where this coefficient and that coefficient is non-zero and all the rest are 0, say. And this is how I'm going to learn about what's happening in high scale physics. So let's start with this plot here, which is very simple. This is a plot to this operator CH box, which actually contributes to the Higgs kinetic energy. And this is the coefficient function CTH. So this is the operator that contributes to the Higgs-Yukawa coupling to the top quark. Here is a fit to data, and the fit is actually a little bit old, but it doesn't matter. So the blue is a 2-parameter experimental fit, to these particular coefficient functions. And then we can predict what these coefficient functions would be in a series of models. So if I have as my new physics at the high scale, a real scalar singlet, I'm forced to lie on this magenta line going over here. So if I measured that these coefficients were over here, say negative, then I would know that I couldn't have a real scalar singlet. On the other hand, if I had a real scalar triplet, I'm forced to be on this yellow line. And if I had a complex scalar triplet, I'm forced to be on this orange line here. So this is the dream, is that by measuring some pattern, I would be able to distinguish between over here and over here. So how exactly do we match this UV theory to the Smeft? Well, let's consider a model with some gauge singlet scalar that only couples to the standard model Higgs. This is my favorite model because it's the simplest model. So if I start with this scalar S, it's got a kinetic term and it's got a potential here. And by playing with integration by parts, it's minus a half S box S minus a potential. And here's the potential, S squared, a cubic term, phi is still the standard model. So I've introduced couplings between my scalar and my standard model. So I can find the classical solution by taking the derivative of L with respect to S, okay, and setting it at the classical solution equals to 0 to find that the classical solution is given by this form here. So if I expand in powers of 1 over the mass of the scalar, I get interactions which are 1 over the mass of the scalar times this cubic term here. I'm going to get a derivative interaction, and I'm going to specifically predict what the coefficients are in this model. So I'll plug this classical solution back into the original Lagrangian, expand consistently in powers of 1 over the mass squared here, and I will predict these coefficient functions. So in this model, I will predict that there are only 2 new coefficients generated. Here they are, phi dagger phi cubed, and phi dagger phi box phi dagger phi. But even better, I'm going to predict what these coefficient functions are in terms of the parameters of the model I started from. So if I measured these at the LHC, if I extracted these measurements, then I could see if they were actually what was predicted in the singlet model. And even though I couldn't see this new scalar, by measuring these coefficient functions, I could infer that there was a new scalar at this high energy. So when we do these EFT fits, now we can do the EFT fits to subsets of the operators. So here's an EFT fit to these two operators, CH and CH box, which are generated in the singlet model. So here's CH box, here's CH, and the green is a combined fit. It's a combined fit to Higgs, dibosons, and electroweak precision observables. So this goes back to my claim that you can't just fit to Higgs physics. If you just fit to Higgs physics and dibosons, you get this outer thing here. And if you include the electroweak precision, you get this purple. And if you put it all together, you get the little green one here. So my global fit would give me this green circle to these two things. But in a model, I can only get, as I've shown you, certain coefficient functions. So in the singlet model, you have to lie on one of these lines down here. So if I measured over here, it couldn't be the singlet model. If I measured right here, it could be the singlet model with certain values of the parameters. So then I can go over here and turn my study around, take my fit to the coefficient functions and express my fit in terms of the parameters of the model I started with, because of course, the coefficient functions are predicted in this model in terms of the parameters of the model. So then I can take my fit and I can extract information about the model. So this is the real gleam in the eye of everyone when they're doing EFT fits, is that you measure these coefficients and you measure something non-zero, and then you take this non-zero measurement and go a step back and say, well, what kind of UV complete model could it give me? What could it come from? So in this case, you can see that there are limits here. And of course, you can do this for any kind of model. It's only been done for rather simple models, but the principle is the same. So at the moment, there's a whole industry of people who are trying to do this at one loop, because of course, what I described here, this is very nice and very simple. But of course, you actually want to do this matching to the EFT at one loop. So you can derive programs that attempt to do this in general at one loop. So this is a very, very active area of Higgs physics and EFT research now, trying to connect the UV complete models to specific measurements. The other thing you should note when you stare at this is that what's wrong with this? Well, it's only got the dimension 6 operators. And of course, as I've said, well, you probably need the dimension 8 unless you have some argument that they're not relevant. And of course, including the dimension 8 operators is quite a bit of work. We now have a complete basis for the dimension 8 operators, and people are starting to include them in various studies, but it's very much a work in progress. So this is very much something that's really ongoing. So by measuring this pattern of coefficients, the goal is, like I said, to understand the scale of new physics. And this can restrict the high scale fits. So this is an example of looking at the scale of new physics and interpreting in terms of the coupling strength in the particular model. And it's only fair to say that the models included here are extremely simple toy models. Doing this in general for real models is something that the community is working on. So I'm going to stop here with the power of the Smeft in my mind. And that's that you can take Higgs decays, you can take top quark interactions, you can take diboson production, you can take LEP physics, and they're all described by this overlapping set of operators. And then you can generate these coefficients in UV complete theories. You can connect the coefficients from the UV complete theories to your measurements. And since Smeft is a consistent field theory, it can systematically be improved by including loop corrections. And of course, there are negatives to this approach from Higgs physics or anything in general, and that there are too many operators. There are a lot of operators for these global fits, And it's difficult to define consistent criteria for the range of validity of the EFT. As I mentioned, there's no consensus in the community. And these higher dimension operators, one also has to think about. So this is a great time to be doing EFT physics and EFT physics for Higgs physics, because there's so much to do. If we don't find a new Higgs boson, this is the way we're going to learn about Higgs physics and UV complete theories. And there's a lot of work to do. So I'm going to stop here. Thank you.
Thank you so much, Professor Dawson, for this beautiful and clear explanation of the basics of HFT. Questions, please. Okay, Ognivo.
Hi, so I have just first question was that you said that when we ruin the coupling to the gauge boson to the Higgs, so that will obviously violate the unitarity in the SMEFT scheme. But can't we argue that if the unitarity violation happening in a very high scale, we can always argue that some new physics will come and take care of the unitarity in that limit?
That's exactly the point. The point is that then that would say that there's some energy scale that the EFT is not valid above, or that my expansion is not valid above. So absolutely.
So it is basically like similarly getting a Lee-Quick-Thatcher bound for EFT basically.
It's exactly Lee-Quick and Thacker. Lee-Quick and Thacker said that if we didn't find a Higgs, there was unitarity violation at 3 TeV. So the Smeft would say that I'm putting in these new operators, unitarity is violated. So then there's some upper energy scale at which the cutoff is no longer good. And this is, let me go back to this plot. Sorry, I have way too many plots. That's because I'm excited. So this is W pair production. So you can see these effects growing. This is log scale here, growing, growing, growing. And this is some random collection of 3-gauge boson couplings and so forth. So you have to take these and check, see, is unitarity valid? In this particular case, I did check. But in general, it tells you that there's an energy cutoff. Absolutely.
Okay. And
I like describing it as Lee-Quick, Thacker, or Smeft.
Okay. And another question was that in the beginning, when we are moving from the old Kappa framework to the new framework, where we are explicitly writing the each EFT operators, and if we now use this technique to the Kappa framework result, so there are some identity is emerging between the coefficient of the various operators. So does those pattern help us to make new model building, that because a similar structure can be found in Higgs to other particles coupling in the standard model also, because all the gauge boson coupling comes from the same term, or even the fermion also. So does those identities will help?
Yes and no. Okay, so here's H to BB bar. Okay, so yeah, okay. So this is just a kappa, right? It's just the kappa frame here. So this is what I was talking about in the end, that the really interesting thing is to predict these coefficients in certain models. So you say, we measure the coupling of H to BB bar and it's a little bit off, right? Can I learn anything? You say, I'm going to construct a model which generates this operator. And then I'm going to take the predictions of that model with that operator and see what it does to the other couplings. That's where I was going at the end, where I was talking about taking your UV complete models, whatever they may be, and connecting them with the Smeft fits, because that's what we really need to do. But right now, our data is not precise enough to do that.
Okay. Thanks.
I have a question.
Yes, please go ahead, Muniman.
So, I mean, you were showing this Higgs to ZV or Higgs to Z effect burden. This ratio, the ratio with respect to SN prediction. So I'm just wondering that we don't have any contribution from, let's say, dimension 5 operator. Because that
I'm sorry, I can't hear you.
Yes. So dimension 5 operator will not have any contribution at any order in this.
Oh, the
So
dimension
dimension-
5,
Yeah.
the dimension 5 operators violate lepton number. So I'm assuming that lepton number is conserved.
I see. So with that assumption, this is okay. Okay. But if
These
you,
are
for
true.
example, consider the lepton number violation, then basically that has to be included, right? Am I correct?
Right. I mean, they're very interesting studies where they consider models with lepton number violation. And these studies, of course, connect with neutrino physics. So the neutrino physicists do almost exactly the same thing as the Smeft here, because they're looking for new physics with lepton number violation. So they have the dimension 5 operators.
But if I consider that, then I guess this Higgs to Z FF bar particularly, that operator can also contribute, possibly.
Well, that would contribute to Z to say E mu, which, you know, probably pretty good limits on it.
Okay, thank you.
Hello.
Yes, please go ahead.
Okay, so I have just one basic question. So in this standard model effective field theory, in dimension 5, apart from this Weinberg operator, do we have any other operators?
No, it's just the Weinberg operator with the Higgs.
Then there cannot be any contribution to H going to GFF bar, right? Because we have to write effective operator, we have to write W mu. So that will be dimension 6, I guess.
Yeah, I don't know. I've never worked it out. You're probably right. But it could be with two insertions.
But that will be some higher
I would have
dimension.
to work it out carefully, but certainly that's something that people have not considered, since we know experimentally that that's not relevant.
Okay, thank you.
Anybody else?
And yeah, I have a short question. So I think
Sure, sure.
at the very beginning, you were showing this this kappa framework, some plot where this the top quark, I mean the kappa T, I think was negative, right?
Oh, yeah. Oh, and you want to know how it could be negative?
Yeah, if you have some particular comment on that.
Yeah, that's actually really interesting, because it comes from the fact that we measure kappa T in TTH where it's squared, right? You calculate the amplitude squared, but you also measure in single top production. So in single top production, or single top production, you're sensitive to an interference term, which can get the sign SIGN. So it's all from a single top. Because experimentally, those are combined. You think of it all as being TTH, but there is a little contribution from single top.
Okay, thank you.
Anybody else? I don't see any hands. I have one or two stupid questions. One is
No
that,
question. But you're not allowed to describe questions.
no,
as to-
actually, I'm extremely happy that I understood at least some part, because all these days, these EFT, AGFT, how things are being done, it was not clear to me. Today, I am very happy that at least some basic parts I understood. So my question is, we need both total cross-section and differential measurements? Differential cross-section
Absolutely.
measurements? Yeah, both are needed.
Yep.
Yeah, and of course, those with larger branching ratios and cross sections, so we can afford to have differential measurements. Otherwise, it will be only, yeah.
Actually, let me
So
show you.
the point, yeah.
I have a cool plot, which I didn't show. So let me show you my cool plot, and then you can keep going. So this is WZ production as a function of the cut. So it shows you, and this extracted
yes.
length on an EFT.
Mhm.
It shows you as you change the cut. So as you go from the high scale to lower cut, your fit changes. And that you get most of the oomph of your fit from the highest energy scale that you probe. So, sorry to interrupt. I just like this plot because it illustrates.
No, this one. Yeah, okay. And but in general, it will be always true, isn't it, that on the higher side of these distributions, more interesting features may come up. Although they are
Absolutely.
much more sensitive, one can say.
It's
So
always
in
the
this,
high.
yeah. And in this context, then how do you compare this EFT analysis with the STXS analysis?
Well, you know, it's really important for the experimentalists not to have an overflow bin at the top, right? Because if there's no overflow, so you know the top energy in each bin. So you can do the EFT fits with the same cuts as the STXS, right? Because you can take your fit and just put it in the appropriate kinematic bins. And in fact, people have done that.
Mm-hmm.
So as long as the data is presented in specific energy bins, i.e. no overflow at the top, it can be compared in a straightforward way.
And again, the point is that what will be the optimum? There is no optimum number of distributions. More it is better, of course.
Yeah, more is better. Sorry.
Better, of course. Yeah. Because already you have quite a few coefficients to measure or to estimate. Yeah. Okay.
Well, it's not only more distributions, but more processes too, because each process
definitely involves different
things, right?
Yeah. So I think for the time being, we are fine. Monimala, is it okay? So let's thank the speaker. It was a beautiful talk, and thank you so much.
Thank you for having me. It's always a pleasure.
Hope,